Let's talk about a huge shift in the world of software. We used to have this image of the lone genius coder crafting these perfect, complex little pieces of logic. But that's just not the world we live in anymore. Today, we're going to explore why the most critical skill for a developer isn't just about writing code, but about wiring it all together.
So let me start with a question that might sound a little backwards. Why is it that the most important code you'll write isn't some brilliant, complex algorithm, but is actually the simple line that connects one system to another? I mean, it goes against everything we're taught, right? We're supposed to value that clever logic. But what we're about to see is that in our modern, sprawling, interconnected systems, the real secret to success, the thing that separates a resilient application from a house of cards, is all in the wiring.
And this is where we came from. This was the era of the lonely coder, the hero programmer. Here, value was all about what happened inside a single function or a class. The whole goal was to create this perfect, self-contained little universe of logic. An engineer could spend weeks just polishing one algorithm, and that was seen as the absolute peak of the craft. It was all about the internals.
But that was then. Today, the game has completely changed. The modern developer, you, are a system orchestrator. The app you're building isn't this one single thing you built from scratch. Oh no. It's more like an assembly of hundreds, maybe thousands of different parts. Some are from your team, some are from other teams, and a whole bunch from third-party libraries you've never even looked inside. The real challenge now isn't just writing the individual parts. It's making sure all those different pieces can find each other, talk to each other, and actually work together without falling apart. The entire system's health depends on the strength of those connections.
So, if we're going to be a good orchestrator, we've got to know the instruments in our orchestra, right? What are these building blocks we're trying to connect? Well, in modern software, they really come in two main flavors.
What's really cool about this table is how it boils everything down to one key difference: physical boundaries. On one side, you've got components. Think of these as your local collaborators. They live right there inside your application. A jar file in the Java world or a DLL in the .NET world. You can often mess with them directly, change how they behave. But then, on the other side, you've got services. These guys are remote. They live somewhere else, maybe on a server halfway across the world, and you talk to them over the network. You can't see their code, you just interact with their public face, their API. Now, wiring a local component is way different from wiring a remote service, but the philosophy we're about to dive into applies to both.
Okay, so if our job is to wire all these pieces together, how do we do it? Well, the first way you might think of, the most direct way, is actually what I call the hard-coded trap. This is an idea called tight coupling, and I'm telling you, it is probably the #1 cause of headaches and maintenance nightmares in software. Let's walk through a super simple example to see why this approach just fails spectacularly.
And here it is. Look at that. One little line of code. It looks so simple, so innocent. We've got a car class, and our car needs a driver, so what do? We just make one. New driver. Boom. Done. At this exact moment, our car class is now responsible for creating its own driver. It is tightly coupled to the driver. The car now has hard-coded specific knowledge of exactly how a driver is born. It seems so easy, so direct, but we've just set a trap for our future selves.
And here's where the trap springs. A few months go by, and a new business requirement comes down the pipeline. And it's a totally reasonable request. From now on, you can't have a driver without a valid license. This means the recipe for creating a driver, its constructor, has to change. It can't just be new driver anymore. Now to create a driver, you have to provide a license object. And this is the result. This is the pain. The second that driver's recipe changes, our car class just breaks. It won't even compile anymore. That line, new driver, is now an error. But wait, it gets so much worse. It's not just the car. It's every single place in our entire system that ever created a driver is now broken. A single logical change in one file has caused a ripple effect, a cascading failure across the whole application. Now we have to go on this awful bug hunt, tracking down every single instance of new driver and fixing it one by one. Our system isn't resilient. It's fragile. It shatters at the slightest touch.
This fragility, this constant cycle of fixing things that break unexpectedly, that's the problem we have to solve. And the solution isn't just some clever new pattern, it's a complete 180-degree flip in how we think about who's in charge in our code. It's a total philosophical shift.
So, how do we escape this trap of cascading failures? How do we build systems that can actually adapt to change instead of just breaking? The answer is to take that whole model of creation and just turn it completely upside down.
It all comes down to this one simple, famous phrase known as the Hollywood principle. You know, when an aspiring actor goes to an audition, the casting director tells them, "Don't call us, we'll call you." The actor isn't in control. They don't get to decide when they get a job. They have to give up control to the studio and wait for the call. We are going to apply this exact same idea to our code. Our car object will no longer be in charge of creating a driver. It's going to give up control.
This big idea has a fancy name, Inversion of Control, or IOC for short. In our old brittle code, the car was in charge. It decided when and how to create the things it needed. With IOC, we invert that relationship. We introduce some kind of higher power, usually a framework, that takes over control of the whole process. The framework manages the flow. It creates all the objects, wires them together, and only when everything is ready does it call our code. So the car no longer says, "I'm going to create a driver." Instead, it just declares, "Hey, to do my job, I need a driver," and it trusts the framework to provide one.
So this is a really crucial point. If inversion of control is the what, the philosophy of giving up control, then dependency injection, or DI, is the how. It's the actual practical mechanism that brings IOC to life. DI is the process where that external container provides or injects the driver into the car. Instead of the car having to build its own driver, the container builds the driver and its license and then just hands the finished, ready-to-use driver to the car. The responsibility of creation has been moved out of the car and into the container.
Okay, I know this can still feel a bit abstract, so let's try a couple of real-world analogies. Think about going to a restaurant. In the old tightly coupled world, if you wanted an omelet, you'd have to go into the kitchen yourself, find the eggs, find a pan, figure out how the stove works, and cook it. You were coupled to the kitchen's messy details. In the IOC world, you just sit down at your table and tell the waiter you'd like an omelet. The waiter, who is our container, takes care of everything behind the scenes. And a few minutes later, a finished plate just arrives at your table. You don't know how it was made, you don't care about the details, you just got the thing you asked for.
Or how about this one? A big construction site. A skilled bricklayer's job is to do one thing really well: lay bricks and build a perfect wall. Their job is not to spend half the day mixing mortar or trying to build their own scaffolding. That's someone else's responsibility. A good foreman, our container, makes sure that when the bricklayer shows up, the scaffolding is already built, the bricks are neatly stacked, and the mortar is ready to go. The foreman provides everything the bricklayer needs so they can focus on their actual job. That is exactly what dependency injection does for our code. It lets our classes focus on their specific business logic, not on all the logistical setup.
Now, let's zoom out for a second. This idea of wiring things together isn't just for tiny objects inside a single application. This same exact philosophy of letting a container manage all the connections scales up to the macro level. It's how we wire entire applications together into a massive, working system of services.
And this is exactly where modern frameworks like Spring come into the picture. They are the sophisticated foremen, the expert waiters for our applications. They provide all the underlying plumbing, that automated assembly line that handles the entire life cycle of our objects, or beans in Spring terminology. The framework just reads our configuration, sees that a car needs a driver and that a driver needs a license, and it handles that whole complex chain of creation and injection for us. All that logistical work is just handled. It frees us up as developers to focus on the things that actually matter to the business.
So why does all this matter? Why did we just spend all this time on one line of code and a few analogies? Because understanding this shift, from manually creating everything to having it injected, isn't just a minor technical detail. It's a fundamental choice an architect makes. And it's the choice that determines if your system is going to be flexible and easy to maintain, or brittle, fragile, and incredibly expensive to change.
So let's just quickly recap the huge benefits we get from this. First, we get loose coupling. The car doesn't know how to build a driver anymore, and it doesn't care. That separation is everything. Second, it makes testing so much easier. In a test, we can just tell the container, hey, for this test run, don't give the car a real driver. Give it this fake, mock one that I can control. This lets us test the car in total isolation. Third, this all leads to amazing maintainability. Our system becomes resilient, the driver's recipe can change, and the car doesn't break. We just change the wiring configuration in one place. And finally, and maybe most importantly, it gives us focus. Just like that bricklayer, we get to concentrate on writing the code that delivers real value, not getting bogged down in logistical nightmares.
So I want to leave you with one final thought to take with you. The next time you're working, take a look at the systems you build every day. Look past the fancy algorithms and the complicated business rules for a second. Look at the seams. Look at how things are connected. And ask yourself, are you building a house of cards where one tiny change in the foundation can bring the whole thing crashing down? Or are you building a fortress, a resilient system that's secured not by the strength of its individual bricks, but by the thoughtful, flexible, and powerful wiring that holds it all together?